We're talking about accelerated motion, right? This whole chapter is about accelerated motion. Now, we could still ask a question and talk about motion that isn't accelerated because that was what was in the last chapter, right? So you're going to recognize in this course that the course is cumulative. There could be something from the last chapter that shows up in this test inherently, just like math when you build upon something. But the general idea for this test is accelerated motion, not constant motion. So what do we mean when we say accelerated motion? What is changing? What's changing?
Velocity.
Very good. Velocity is changing. And remember, everything changes as a function of time. Everything. You can't stop time. If you could, that would be a whole other ballgame, right? If you could actually stop time. But everything that changes is always a function of time. So because velocity is changing with respect to time, we say it accelerates. It goes from some initial velocity to some final velocity. The major keys to this chapter, or the major key point, was recognize when the problem starts and when it ends. I've emphasized that a lot now. I've talked about that a couple times. There was a problem set question I want to quickly talk about where the person who's running and then decides to slide into the base to see if they can get into the tag in the baseball game. And as the person runs, the person has some initial velocity or some velocity they're running at a constant rate. And then, I think it's a she actually, the problem. I think she starts to slide into the base. So as the person starts to slide is when the problem actually begins. So we have somebody running and it was at some velocity. It was like, I think 5 point something. But then the person starts to slide over here. Okay? And they start to slide a given distance from here all the way to the end into the base. This is the beginning of the problem. And this is the end of the problem. This is either homework or a problem set question. Somebody asked about it office hours yesterday, and I thought it was a good question to start with. Okay. Is it coming in there? I don't know if it is or not. You guys getting wet in the back? No or not? Yeah, I guess so the key here, the key is to recognize when the problem begins and when the problem ends. So, I'm going to ask you for questions, but what I thought I'd do for like maybe 20 minutes is discuss the key ideas that I think you should know for the test. The other class has a double today, so they have an extra period of review. They're just going to do practice problems. But I also haven't gone over the calculator stuff with them yet, so it's not going to be a full extra period. But they're going to have a little more time. So I want to emphasize some things that I think are important that we might not have time to discuss if I don't point them out now. So when an object starts on the launch on the way up and then returns back to the ground afterward on the way down, we have to consider the fact that this object itself, when it gets to the top, what happens again? It stops. It stops at the top. So remember, for problems like this, you can think of the first half of the problem from here to here as part one. And then the second half of the problem on the way down as part two. You can break it into two parts. Now, what can be a little bit confusing is the subscript for velocity, because you're going to use several velocities here. On the first part, you have initial velocity at the ground. You're launching it, right? And then what's the final velocity in the first part when it gets to the top? What's the final velocity?
Yeah, that's like the height.
What is the value of zero specifically? Zero, because it stops.
Okay.
But then on the way down, it starts with zero velocity and it ends with some velocity. We did one of these problems already, but I want you to recall in your mind how you break it into pieces. So this might be VI, and this is VF here, and VF is equal to 0 for the first part of the problem. But on the way back down, that's the initial velocity now at the top, and it's 0. And the final velocity is what we might be determining at the end of the problem. So I want you to recognize when you break parts of the problems into pieces, the final velocity for the first part is going to be the initial velocity for the second part. Think about who runs cross country. That's a great example for this. All right, so in a relay race, when you hand off the baton, so you, Brish, say you're handing off to Danny, you're doing a 4x2 or something, right? You're running. The velocity with which you hand it off to Danny is your final velocity of your leg of the race. That's his initial velocity because you have to be moving together. Remember how when you hand off in a track race, you're both moving and you hand it off smoothly. It's not just like you hit it to the person. Right? You're both starting to run, and then you hand off. So that your final velocity is his initial velocity. That's what we're saying here. So if an object is struck and it starts to move, and then it encounters friction, well, the final velocity of the first part at the end of here, and then it starts to encounter friction, that'll equal the initial velocity of the part where it encounters friction. So we could have a problem such as this, where this part's A, B, and C. Let's say that a car, my artwork is terrible. Okay, there's a car. Let's say a car, that's not bad, right? Let's say that's a door and there's a windshield. So the car is going to the right. It's fine, it's fine. Now, listen. The car is accelerating with positive acceleration. The car is accelerating with positive acceleration. It's got some initial velocity. Listen. It has a final velocity after it goes a certain distance. Now, let's say that this car, listen carefully, let's say that this car, after undergoing a certain distance or a translation here, encounters oil in the road. Okay, the oil spill will reduce the amount of friction, right? Will reduce the amount of friction here that's actually occurring. So this car might actually, in this case, start to accelerate with a different value. It might still be positive. It might be negative. Now, it would be negative acceleration if it was encountering like sand or dirt, something that would physically slow the car down. Because it's oil, it's just going to change the acceleration. But the idea here is that you have some initial velocity, some final, but the final velocity of this part becomes, again, the initial velocity of this part. So you might have to break the problem into pieces. And we've talked about this a couple of times, but to recognize that you want to make it simpler on yourself, right? Make it easier on yourself. So if the problem has parts A, B, and C, like I instructed, what you should probably do, go in order in which I'm asking the problems. Because there's a good chance that part A affects part B and part B affects part C. Okay? Trying to think of other problem-solving techniques. Because I find that using the formulas you guys are good at, I've noticed, right? Once you can figure out which formula is not as hard, but it's physically encountering the problem and understanding what to do based on the context of the situation. So this is an example, maybe again, this is like dirt now, and the dirt slows the car down, so now it feels negative acceleration. Or maybe suddenly a parachute is ejected out of the back of the race car, and after it's going super fast for a while around the racetrack, the parachute gets ejected and suddenly it decelerates to rest. Yeah.
So it's going to be a lot of problems.
You could definitely expect math problems, yeah. I mean, every test is generally a third, where you have multiple choice, short answer, like conceptual mainly, and then mathematical word problems. The multiple choice could have math in them, but it would be very simple math. It would be very simple math. Or it might be conceptual, but using numbers too. Like, for example, here's a great problem to know. We talked about this example. If an object is launched from the ground with some initial velocity, say 20 meters per second, when it returns, what's the velocity going to be when it hits the ground?
The negative.
The negative of the initial velocity. Remember the symmetry in the problems? That's the kind of problem for multiple choice that if you do all the work, it'll take you about 5 minutes. But if you know that there's symmetry in a problem, when it's launched from the ground and it comes right back down to the ground, the symmetry that exists tells you that if its positive initial velocity is 20, then on the way down it will be a negative 20 for the final velocity when it hits the ground. We also know that there's symmetry. So on the way up, if it takes 2 seconds, what can we conclude? It takes 2 seconds on the way down. If you have the total time of flight, the rush is 4 seconds, then on the way up, the time of flight is 2 seconds. Again, the major assumption is that there is no air resistance. That's the only time there's symmetry in these problems, which again, in reality is not the case.
You kind of answered my question. I just want to know, like, if you state a problem, how would we like symmetry?
So if it's launched from the ground and it ends on the ground.
Okay.
Pretty much, if it ends at the same spot as launched from, I shouldn't say the ground, because I can launch something from the height of a table and it ends on the table. As long as its y displacement is 0, meaning it starts where it ends, there's always symmetry in those problems. But if it's launched from the ground and it ends on a cliff, or launched from a cliff and ends on the ground, no symmetry in those problems at all. Okay? Alex?
Will you give us anything with air resistance?
I'm going to ask you conceptually about it, but mathematically, no. Again, so the math problems will not involve air resistance. But conceptually, you should understand what air resistance does. You should understand how it works. I've talked about terminal velocity, how velocity keeps getting greater until air resistance is so much that it just starts to coast. I've talked about how air resistance lowers the effect of the acceleration. We saw that in their lab results. Acceleration of 8.9 instead of 9.81.
Can we finish going through the problem where it's like launched from something and it lands on?
The lava ball.
No. It's like you gave it to us at the end of our slides.
For 3-4?
Yeah.
Absolutely. It's launched from the ground and it ends on a cliff?
It ends over something.
Let me pause and get... All right, so this is from 3-4, so we're just going back to this. And Emily, if you remind me, what was the question being asked? What time will it reach 15
Yeah,
meters?
how long will it take to reach?
So how many answers did you get? Because I noticed a lot of people got several answers here. Alex, how many did you get?
You get 2 because it passes it on the way up and then also passes it on the way down.
Yeah, take a look at this object. Take a look at this image. On the way up and on the way down, this object itself crosses a height of 15 meters on the way up and then again on the way down in both of these spots. So your time will be 2 answers for sure. And let's figure this out. So it's y equals VIT plus 1/2 AT squared. Why didn't I use the VF formulas? Why didn't I use the VF formulas? Yep. Yeah, you don't have final velocity in the problem. Now, yes, we have the final velocity when it reaches the ground will be -20. But we don't care about when it gets back to the ground. We care about when it gets to a height of 15 meters. So Gigi, you asked about this earlier. This is not symmetry because we're not completing the problem. We're not ending up back on the ground. We're stopping at a height of 15 meters in this problem. So although it's launched from the ground and eventually it would end on the ground, this is not showing symmetry because we've kind of stopped the problem. We stopped the problem right here when it gets to that point. That's the end of our problem. And it happens twice. Again, once here and then once at the very end. Yeah. Yeah, guys, so any vertical motion question can be given. I can vary this and say that it goes to 35 meters. I can vary and say that it's launched from a given height, and I ask you when it's going to get to 20 meters. So maybe the ground is here, it's launched from here, and I want to know when it's going to get to here. Well, you have to know what your displacement is in that case. So in this problem, what is my vertical displacement? Whether I'm on the way up or on the way down, where you see blue writing, we are 15 meters above where we started. So the y value in this problem is 15. The y value is 15. And again, this object reaches a height of 15 meters twice. Once on the way up, and then again on the way down. And then again on the way down. And we could do another one after this where we launch from the cliff and go down. That's fine too. Initial velocity is 20. T is unknown. Acceleration is negative 9.81. And T again is unknown. So I take a look at this problem and I recognize right away that it's a quadratic. If, you can write a note for this, we've already mentioned it, you can write a note. If this happened to be 0, if the y value happened to be 0, then it's the problem with symmetry again. And we could also just drop this off and factor out t. Factor t out and solve this by hand. It's a lot easier. But because there's a constant of 15 over here, I have to move the 15 over. And when I move the 15 over to the right-hand side, the equation becomes a little bit messier. I now definitely have a full-on quadratic. Okay? Without the constant term, I can easily solve this by factoring out a GCF. But as soon as the 15 is there, now I have to use either the quadratic formula or graphing to solve. I personally don't like to take the time to do the quadratic formula by hand. So I would graph this. So in y1, we're going to type this in right here. And remember, wherever you see a t, you simply put an x. For t squared, you put x squared. And then I would graph this and find the x-intercepts. I know that the times have to be positive, so I already know what your graph, I have an idea of what your graph will look like already. I know it's going to be positive time. I don't know what that time will be, but I do know that it will be a positive time. The graph's going to start down here at negative 15, and it's going to be concave down. So that's definitely the shape of the graph. I just don't know what the numbers are. So I'm giving you guys a couple seconds here to go ahead and figure out what are the x-intercepts for this graph. Where is the height equal to 0? Here and here. And what times does this occur? At what times? And
Oh, I was just gonna ask, how do you do that? How do you
I don't know if graphs look like that, or
how do you plug that the 3 numbers into
You
that?
did it in class.
When? Right answer.
values. And I presume 6. It always gives me standard. Yeah, zoom 6 gives you the standard zoom on the graph. Yeah. Now you need to find those x intercepts. See that? See that? Second. Calculate. And then go to 0. Yes. It's going to say left bound, which means take a guess, pick a number to the left of this root. Right down. Then you pick a number to the right of this root. Don't go beyond these arrows, it's going to search for a root, which means if you put this arrow in here, it's not going to know which one it is. You know what I'm saying? Enter what it says next. 1 second. Same thing for this root. It's the left arrow, the 2, and the right arrow, something over here. The answer is that time. The t value is just that will make it like 0. Yeah, so if I were choosing the second, for the left hand, for the left hand, this first one. So if I'm choosing the left hand, I can go any number of the left one because there's no other root. But I can't go beyond -10. So I'll choose like negative. I don't use a cursor. Yeah, I'm on my video using a cursor. It's easier to type in. Right down, I have to pick a number to the right of this root without going beyond this root. So I'm going to choose letter between, which is 2. Because that's the next intercept. That was not. Yeah, so you just count over. Hit enter, it says guess. Hit enter one at a time until you find out where it is. And this is what we went over in class when I did on the computer. You could use trace, that's fine too, but trace doesn't give you an exact answer. Are you pressing second calc first, then tracing, you said? Yeah, you do that too. You go below the axis and then above the axis, and it finds it between.
How would you know which one?
I put up a whole video on that. I didn't teach that part. So there's a whole video on that for all those who's online. Dimensions?
Yeah,
so that means that you go through block, turn that off. Go up to it, get enter. Guys, don't lend your calculator to other people because a lot of people lend it, and they get back and it's not the form they wanted it. So if your plots are off, your plots are off. If you want to show me, you can also go up.
I don't remember how to like do it.
Yeah. It's on Moodle. I put the whole guide on Moodle and the documents and handouts. Yeah, the guide that we worked off of in freshman year. Yep. Okay. So we have 2 answers. Alex, what was the second answer after point? Yeah, that one? So, 3.06, you use the calc tool to find it? 3.08.
Yeah, wait, I had 3.1. Is that it?
Yeah. He said 0.8. Yep, that works. So, we can continue doing this, but I kind of want to move on. It's your time, guys. It's your time. You can watch a video on how to do this later and use that time later more wisely. We're not going to start until we're all kind of focused, you know? Again, I put a video up on how to do this on Moodle. It's on the videos in class. Just take a look at it. It's fine. Okay? I wouldn't waste your time on the calculator part. I'd rather go over the physics part, which is a lot more important and harder to learn. Then you can watch a video later on this calculator. All right, so let's look at an example of a problem now. First of all, let's write our formulas down on the next slide. I listed our formulas there for this chapter. So our formulas for this chapter, in reality, we have x equals VIT plus 1/2 AT squared, or, as we recall, we can also just write y equals the same formula. You're only going to be given this formula on the formula sheet, what's boxed in. But you have to recognize that if it's vertical motion, you change x to y. The second formula doesn't matter whether it's x or y. It's the same formula. There is no displacement in this formula. The third formula, though, it does. So that's how it's given, or you can write it with a y value. Now, there's a lot of stuff to point out. So you might want to jot these notes down I'm going to give you. They're not shortcuts, but they're things to recognize that make the problem easier. So, first, whenever it's a free fall, VI equals 0. I would probably write the word free fall down in my notes. I'm not writing everything down. I'm just writing the key components. But in a free fall, initial velocity is always 0. That's when you drop something or from max height on the way down. And when this happens, suddenly these all drop off. These all drop off, which make the formulas a lot easier to work with. So in a free fall, recognize that this affects all three formulas. All three formulas become much simpler whenever you're looking at a problem from the peak to the way down. So it could be a problem like this, where all we care about is from A to B. Or it could literally just be an actual free fall from A to B. So again, it could be launched from the ground, but if we're breaking it into pieces and we do the first way on the way up and the second half on the way down, if you do on the way down by itself, it's identical to a free fall. It's as if you're physically dropping it. This is what I'm referring to, this red highlighted region right here. Okay, on the way down. And that's a big, big thing to make your equations easier. Second piece. Second piece. So that's the first thing. When looking for something to do with max height, so let's jot down for max height problems. For max height problems, VF is always equal to what? When it gets to max height, what's the velocity? 0. So for these problems, for the max height problems, what we'll recognize is that we get 0, and that would affect this equation and this equation, and make them a lot simpler as well. Now, if it's a max height problem, it's really vertical motion, so it's really this equation, but it's the same thing. Right? These are the same equations, it's called x, y. But I want you to recognize that on a problem that involves find the time to max height, you could just set VF equal to 0. Because at max height, the velocity is 0. Whatever the initial velocity is launched with, that goes in for VI, instead of 0 for VI. So again, the second type of problem is the max height problem. So we've got free fall type problem, or on the way down. We've got the max height problem, also known as on the way up. Right? On the way up, you see other different parts of the problem. On the way up is the max height problem, you get the max height. On the way down is a free fall. We also have the problem we haven't really had a chance to look at yet, where we start at a height, we're launched up, and then it comes back down. So let's take a look at that kind of an example here. So let's start at a given height instead and launch it upward, and then see what it looks like coming back down. Daniel.
Is that the lava one in the problem set?
I think there was one with lava, and it erupts from a volcano, right? And you want to figure out what were you actually looking for in that problem, Daniel? Do you remember?
It's like 2 seconds, like it's upward direction.
Was it the time to get to
The speed and what direction it was going in.
after a certain time or at a certain height?
After 2 seconds.
After 2 seconds. So I'll vary it up a little bit for this one. Gigi.
I just have a question. When it's asking for speed, are you going to calculate?
Remember that in this chapter, guys, listen to this. Remember that in this chapter, when it asks about speed, because this is all one-dimensional motion, it's either up or down. So if they say find the speed, it just means find the velocity, but you don't have to get the sign. So if a problem says, find the speed with which it hits the ground, you could just say 5 meters per second. But if it says find the final velocity, and it's about to hit the ground, you should say negative 5 meters per second. Remember that speed does not care about direction. Speed is only the magnitude of your velocity. It's only the quantity, not the direction. So if I'm about to hit the ground, that's 5 meters per second in speed, or negative 5 meters per second in velocity.
So you're calculating basically just the velocity.
Yes. Whenever it says find speed, you're finding velocity. Exactly. Whether it's initial or final, you're finding velocity. That's right. It's when it changes direction we have to care about speed versus velocity. But here it doesn't. It's going up and then straight back down. And I mean change direction as far as curving.
The last problem in the problem set said find the speed and direction. Is that just velocity?
Exactly. Exactly. So that's a good example, Gigi. What problem was that?
61.
Problem number 61 says find the speed and the direction. So the speed is the final velocity, and since you got an answer of negative, the direction is probably down in that problem. Is that correct? Is it down? Okay. Either way, it doesn't matter.
Direction's like this.
2 is up and 3 is down.
All right. Let's take a look at this problem. Let's say that this has a height of 25 meters. This object, let's see, can we do this way? This object is launched with a velocity. Well, what if we make the velocity unknown, actually? Yeah, let's make the velocity unknown. This is launched with some unknown initial velocity. It takes 1.5 seconds to get to max height. So our goal in this problem is let's figure out what initial velocity should this be launched with for it to only take a second and a half to get to max height. And then, so again, part A, what is VI? And then part B, find the impact velocity. So we're not even asked in this problem about what is the max height. We're just asked to find the initial velocity of this problem. Now, if we take a look at our equation and think about this problem as only the way up, I need you to do this. If you need to highlight it like I am. Highlight only the way up for now. What's in green is what we care about right now here. I highlighted the way up. What we'll recognize is that when it reaches that max height at the top, what is the velocity when it reaches that max height at the end of our problem? Good, 0. Remember, this is the end of the problem, and this is the beginning. This is for part A that I'm caring about, okay? For part A. Why do I not consider the ground the end of the problem? Because the problem gave me something about the time it takes to get to max height. So that's probably useful. It's probably very useful to figure that out. So for this problem, I can consider, well, I have for part A, I have the fact that VF is equal to 0. I have the time of flight is 1.5. Acceleration is always negative 9.81. So as a result, for this problem, I can go ahead and use one of my formulas to figure out the initial velocity. Which formula would work in this case for part A if I want to find initial velocity? Which of the three formulas? You can look at your formula sheet if you need to, or look at your notes, maybe swipe back to your notes a little bit. There's only one formula that would be useful to find initial velocity for part A. Only one of them. What do you got, Zoe? What do you think? Yeah. Now, if the problem asked you to find the max height, then maybe you could use VF squared equals VI squared plus 2AY in a second or a little bit later. Since VF is 0, that drops off. VI is the initial velocity we're looking for. A is negative 9.81. T is 1.5 seconds. This is meters per second squared. Seconds cancels with seconds, leaves me with meters per second. I get a negative number here. I move that negative number over to this side, becomes a positive number, obviously because we launched this object up. Your answer has to be positive. Again, this is a negative quantity, but you're going to add it over to the left-hand side. You're going to add this over to the left-hand side. It's around 15, obviously. What is it?
14.715.
So, that's the velocity with which this object is launched. Only due to the first half of the trip did we solve this. Part B wants us to find impact velocity. What does impact velocity mean? What does it physically mean?
It's like the last velocity right before it's the ground.
Yes. It's the velocity the instant before it hits the ground. Write that down if you didn't know that. It's not the velocity after it hits the ground, because that's just 0, obviously. It stops. Impact speed or impact velocity is the speed or the velocity the instant before it hits the ground. In this case, final velocity is what we're talking about. Final velocity.
So is that just a different understanding of final velocity?
Yes, as long as you're considering the whole problem, or from the top down to the bottom. Okay, as long as this is the end of your problem. Yes,
So we
Alex.
will lose the 25 meters in the end.
Well, let's take a look now. So I could do this problem two ways. Listen carefully, because one way doesn't work, and I think people would try this way. For this problem, a lot of students might try to think of from the top all the way down to the bottom. And it's reasonable to think that. Let me highlight what I'm referring to. I'll highlight in yellow. Actually, you can't see yellow on yellow. I'll highlight in blue. A lot of people would try to do part B by thinking of this as a free fall and only looking at the second half of the trip. And that's a reasonable thing to consider. It is a reasonable thing to consider. Because you know that if it's a free fall from the top, then your initial velocity at the top is 0, and you can find the final velocity. But this formula won't work, because you don't have the time it takes. There's no symmetry, and you don't have the time on the way down. If you try the other formula, if you try this formula here, it's also not going to work from the top down because you don't know the distance to max height. You know 25 is the height of the cliff. But if you're going to use this formula here, let me point. If you're going to use this formula here, you need to know the y value from the top down to here. And we don't know this y value because this height is unknown. We could find it, but that's more work. So instead, what we can do is this. Instead of only looking at the second half of the problem, yes, in the beginning we looked at the first half, now we're going to look at the whole thing. And this sometimes just comes to be second nature, or as you practice the problems more, you recognize when it will and won't work. Again, if I try to look at the second half, this will not work because I don't have y or t for the second half of the problem. But I can use this entire problem. So I'm going to re-highlight it all in green to show you that we're going to use the entire problem for part B. So now, for part B, I can use this formula. And let's show how we can use it down here. I'm looking for final velocity right when it hits the ground. The problem begins at the cliff. Well, what's my initial velocity? We just solved for it in the first part. We got 14.7. So remember, this is now the beginning of the problem. And this is now the end of the problem. So in the beginning, what's the velocity? The initial velocity we solved for was 14.7. So in this formula, I can use 14.7. The key in this problem is to recognize what y is for the whole problem. What is the y value for the entire problem? I know acceleration, I'll put that in obviously. What's going to go in that last bubble right here? What's the y value for the whole problem? The whole problem. You guys answered both a lot of questions. And go ahead.
25
Careful.
meters.
Careful, even more.
Negative 25.
Yes, negative 25 meters. And let's take a look at why that makes sense. You start at the cliff. I don't care where you go, how high up the actual projectile gets. Where does it end though? It ends on the ground. What's the difference from the cliff to the ground? What's the physical displacement? Not distance traveled. Remember, distance traveled versus displacement. They're two different things. Sure, the distance traveled is pretty great. You go all the way up to max height, come all the way back down. So the distance traveled is probably like 50, 60, 70 meters, something like that. But from where I start to where I end up 25 meters below where I started. Therefore, y for the whole trip is negative 25. For the whole trip, y is negative 25. Remember, displacement is your change in position. Doesn't matter what route you take along the way. All that matters is where you started and where you ended. And you ended 25 meters lower than where you started. So that's your y value. And then you can go ahead and calculate VF by getting the square of this, square rooting the entire thing, and getting some number in meters per second. What kind of an answer will my answer be? What kind of an answer will it be? Impact velocity on the way. Negative. Negative. Come on, Alex. You're better than that. Negative on the way down. Okay? So what is the number we get here? What number do we end up getting here? 14.7 squared plus this whole mess that's in negative 77. Agreed? Before or after you square root it?
707 before you square root.
707?
Yeah, 707.
Agreed? Disagreed? Help me out here.
He's unhappy about there because I got a really good answer.
Got me.
Got 77.
I don't know. I'm not saying he's right. I'm asking you guys to verify. That's what I say. Agreed or not?
706.59.
Under the radical?
Not like I haven't
Okay.
square rooted it.
Oh, yeah,
So-
it's 77.
Okay, again, guys, if you're rounding differently, you can't let little changes in decimals bother you right now. If you got around 706 and you, for some reason, didn't round properly, or here you estimated 14.7 squared, then it's different. I would put this all in one line of code in my calculator. This is all one line in my calculator. Whatever the square root of that, what do you got? Daniel?
I got 26.58, but that's like 7 to 7.
All right, so around 26.5 or 6.
Wait,
Okay?
so when you get the positive answer, do you just
Let
make
me-
it? You just make it.
You
negative?
remember, square root is plus or minus. You choose which one. Let me point one last thing out. This is really important. Check this. If this object ended right here, the velocity would just be negative 14.7, right? The symmetry, take a look. If it ended right here, that is negative 14.7. So this number had to be more than negative 14.7, right? And it is, in magnitude. So the answer makes sense. Makes sense of your answers. Again, any hard copies of problem sets? I'm going to ask one last time. No? So it's all electronic. If I get all submissions for problem set 2, I'll put the solution up. But I don't foresee that happening today. I know a couple people are already late.
How do I, because I know your calculations, how do I